Hello, my name is Caleb Freilich, and today I'm going to be discussing my project for Introduction to EOIR Systems entitled A Graphical Development of the Discrete Fourier Transform. This project was a programming project with the goal to reproduce figures from Schmidt's numerical simulation of optical wave propagation in MATLAB, and I was personally intrigued by this project as my knowledge of the DFT FT is dated, and a technical refresh through scripting some examples in MATLAB is always well warranted. But maybe most critical to me in my selection of this course project was my desire to understand convolution with discrete functions. My knowledge of convolution has way more in-depth working with analytical continuous functions. My background is in math and EE as well. And the discrete application is far from second nature for me. Before we get too deep in the weeds, let's just provide a quick refresher on the analytical and discrete Fourier transforms. The analytical Fourier transform, shown on the left, is a mathematical masterpiece utilized for understanding the frequency content of a continuous signal, continuous being the operative word here. The analytical Fourier transform involves integrating our continuous signal, f of x, in the time or space domain with a complex phasor to produce our frequency spectrum, which is magnitude or power as a function of our frequency variable, f sub x. As a mathematician in disguise, I can appreciate the beauty and the elegance of this simple integral. However, as is the case with integration, it can be challenging to find the Fourier transform for all possible continuous signals. However, more important to motivate the need for the DFT is the fact that our understanding of signals in the wild is not continuous. We can't represent a voltage signal or a sound wave as continuous in the finite resources of our computer. And thus the DFT is born. And as we all know, the discrete Fourier transform replaces the integral with the sum, and the input signal is now sampled to account for our discrete representation of continuous signals. As such, the frequency domain is also represented as a discrete function, k delta f, where we have specific magnitude values evaluated at frequency points. This forms the triad of differences between our analytical and discrete Fourier transforms. One, we have spatial domain sampling, we have a finite sampling grid, and then we have sampling in the frequency domain. Unfortunately, the DFT is not a free lunch, and by being forced into the discrete realm, we introduce distortions in our signal, potentially affecting both our spatial and frequency content. The pictures on the bottom right of your screen show the effect of aliasing, rippling, and smearing, and periodic replication on our signals. To illustrate how these distortions occur, let's consider an example function with a known Fourier transform. The text considers g of x, a decaying exponential with symmetry around the x-axis. The Fourier transform of g of x is g of f sub x and is shown below. Now there are three main steps by which our continuous functions turn into finite sampled versions of themselves to form the discrete version of our Fourier transfer pair. The first step is to sample our example function in the spatial domain. This is easily accomplished with a comb function. We know from the convolution property of Fourier transforms that multiplication in the spatial domain is equivalent to convolution in the frequency domain. Convolving a continuous signal with a train of delta functions, i.e. our comb function, is a source of aliasing in the frequency domain, as the spectrum will turn into a periodic function with a period determined by the variable delta. Since we're dealing with finite signals, we'll need to window our continuous function in the spatial domain to account for the limited information that we have in our discrete signal. A multiplication by the rectangle function with L creates this finite signal. Again, utilizing the convolution property, we'll convolve the previous result from step 1 with the Fourier transform of our rectangle window function, which is a sinc function in the frequency domain. This introduces ripples and smearing in our frequency domain due to the nature of the sinc function. Finally, we'll turn our continuous function in the frequency domain into a discrete signal by multiplying by another comb function. This manifests as a convolution in the spatial domain, which serves to introduce periodic replications of our signal in that spatial domain. So let's take a look at the first example, taking each one of these steps one at a time. Before we dive in, it's important to note that there are really 2 or 3, depending on how you look at it, parameters to control when taking a DFT. First is the number of samples to use, the grid size, or our window size, and then the sample spacings in the spatial and the frequency domain. In this first example, we're planning on taking a DFT with 16 samples and a grid size of 0.6 meters, which produces a sample spacing in the spatial domain of 3 3/4 centimeters. In the figures that are shown in the text and reproduced in MATLAB, on this PowerPoint, we've extended the sampling to show what is happening to our continuous functions, little g and big G, as we perform the 3 steps needed to produce our discrete versions of our Fourier transform pair. In this example, we start by sampling the spatial domain, and we know that this causes aliasing in the frequency domain, and we can just barely see the effects of that in the far right image, as the convolution creates an image just outside of our axis limits. Our next step is to apply the rectangular window to our spatial function. And if you look closely at the train of samples in the spatial domain, you can just barely see the effects of the windowing as some of the curvature has been removed and the values outside our 0.6 meter window have been zeroed out. The effect in the frequency domain is quite obvious as we see significant rippling in the continuous spectral content. Finally, we'll sample the frequency domain by multiplying our previously continuous function by a train of impulses. This causes periodic replication in our signal in the spatial domain outside of our window. In the bottom row, we show that the actual sampled signal and its corresponding DFT for comparison to our derivation above. Now, in the previous example, we had a pretty narrow representation of our sample in the spatial domain. What if we wanted to change the window to get a larger spatial sample? How would that change our frequency contents? Well, with a lengthened window in the spatial domain, which is what we're doing here by increasing L to 1.2, our frequency domain window is tightened, and the effect is that we get increased aliasing in the frequency domain. Our larger window does mean that less of our spatial signal is affected, as we see little to no difference in the image on the left. This is also good news when it comes to distortion of the signal through rippling, as the overall ripple magnitude is reduced in the figure on the right. Finally, sampling in the frequency domain allows us to see the spectrum and the signal. And we have a larger spatial signal with less ripple in the spectrum, but our spectrum is much, much smaller in width in the frequency domain. Another variable we can control is the number of samples. Increasing the samples often helps to improve the quality of the result of the DFT. However, it comes at the expense of computational efficiency and speed. In this example, we reset the window length to its initial value of 0.6 meters, and we increase the number of samples to 32. The increased number of samples in smaller spatial grid means that there is virtually no aliasing at all in the frequency domain. Applying our window, we do trace some ripples in the spectrum similar to the first time, and a larger window could help us avoid this issue. Finally, we sample the output spectrum and we produce a very wide and fairly clean discrete spectrum. However, our spatial signal window is still very small. The final iteration involves increasing the number of samples even higher, and also increasing the grid size. So now we're using 64 samples and a 1.2 meter grid spacing. Since we match an increase to the grid size with an increase to the number of samples, we can offset any negative aliasing in the frequency domain and maintain a very, very clean spectrum. The increased window length produces very little ripple at all, as it barely disturbs our spatial signal. So you can see the figure on the left, which shows that the sampled spatial signal looks virtually untouched. And same with our frequency domain. No rippling at all, pretty much in that signal. Finally, we sample the frequency domain, and with an increased window in the spatial domain, we end up with a larger signal with less periodic extension. Overall, these results look pretty good, albeit with more required computational resources. Overall, we notice the following observations. Increasing the spatial grid size reduces the rippling. Decreasing the spatial grid spacing reduces aliasing. And then I realized that the power of information is that the more samples, generally the better the DFT. As I was thinking through this project, I was reminded of the trade-off between reducing adverse effects of taking the DFT by simply increasing the number of samples. And it's easy for me to punch a button in my MATLAB script and see the difference that more samples make, but an actual system like my church's digital soundboard, which has complex filtering operations available at the touch of a button, increasing the number of samples comes with a cost. To get more samples, you either need to force a higher sampling rate or introduce more delay and potentially reverb into the system. At some point it becomes undoable or undesirable, and that's really where the art of filtering really meets the DFT. Through this project, I learned that often the hardest part is the sampling and the indexing. The challenges of matching someone else's work involved some parameter guess and check and careful track of units. I was reminded of how hard discrete convolution is for me to understand conceptually. However, I did form a couple of useful rules through this project. The convolution of a continuous function with a comb function produces a periodic continuous function, and the convolution of two comb functions produces another comb function. Thanks for watching and following along. If you have any questions, feel free to reach out.